We're going to be talking about prospects and challenges of quantum finance. My name is Yanni Gambros. I'm the head of business development for QC-Ware, and I'm joined, as you can see, by two members of our technical team, Anupam Prakash and Adam Bouland. So thank you very much for being here. I'm just going to talk for maybe just a couple of minutes in the beginning and just highlight who we are as QC-Ware for maybe some of those that don't really know us, and also talk about our conference that's coming up next week. And then I'll pass it over to Adam and Anupam, and they will discuss the details of this very recent paper that was published by our team. And they'll go over essentially the high-level overview, and we'll be happy to take questions as we go along. Please post your questions in the Q&A function. So let's go on to the next slide. So we at QC-Ware, everything we do is about getting to quantum applications from the software or algorithmic side. So what that means is that we come to these quantum applications, we try to build practical quantum applications, and our approach is different from the hardware manufacturers. So the hardware manufacturers, every time they make big announcements, it's about building new chips, new solutions, new architectures that provide more qubits or better quality qubits. And as you grow the number of qubits, you want to get to this practical quantum applications. We, on the other side, we are a software quantum computing company. And every time we make a big announcement, it's all about essentially using or going after a problem and using fewer qubits than what was previously the best solution to use, or providing an algorithm that provides better performance than that was previously available, right? And so as we do this, we essentially start closing the gap to what is actually required from for practical quantum applications, but we close the gap from this other side than what the hardware manufacturers are doing, right? So with that very quick level set and very quick high level introduction, let's go to the next slide. Just wanted to highlight that next week on December 8th, we're going to have our 4th annual conference. It's called Q2B, Practical Quantum Computing. It's a 3-day event. Obviously, it's virtual this year. Please go to the website, q2b.us, if you haven't done so already, to look at the agenda, to look at speakers. Q2B is the premier event, and it's actually entirely focused on quantum computing. Next slide, I'm just going to show very quickly the agenda at a glance for this 3-day event. We have some excellent speakers. Actually, the very first keynote opening up Q2B is by Eric Schmidt, former CEO and chairman of Google, and co-founder of Schmidt Futures. We have other keynotes by leading academics like John Preskill, Umesh Vazirani, Scott Aronson, and we also have several industry panels and industry speakers talking about their quantum computing initiatives, talking about the work that they're doing currently, the research they're doing currently, the trying to get to practical applications in the respective sectors. So just since we are doing this, this is a finance webinar, I'll highlight the finance track that we have at Q2B. We have presenters from Goldman Sachs, JP Morgan, and BBVA. And we also have a very interesting technical track, and we have some of the major leaders in quantum computing, companies such as IBM and Google and Honeywell, IonQ, D-Wave, several others are speaking about essentially their approaches, their roadmaps, and we expect to hear many major announcements. So with that, let's go to the next slide. So this is the paper that essentially just came out last week. It's authored by members of our team, Prospects and Challenges of Quantum Finance. And if we go to the next slide, this article basically gives a very quick high-level introduction. If you want to maybe forward it to someone, we had some coverage on this. But with that, I'm going to pass it over to Adam, who's going to go actually into the details and kick it off and give us basically a high-level overview of the different topics we discussed in the paper. Adam.
All right, great. Thanks so much for the introduction, Yanni. So today we're going to be talking about applications of quantum computing in 3 different areas of finance, starting with quantum speedups for Monte Carlo algorithms. So Monte Carlo algorithms are ubiquitous in finance. They have many different financial applications, from pricing exotic derivatives or options to risk analysis, value at risk, conditional value at risk calculations, etc. And the basic idea of these classical Monte Carlo algorithms is that you have some quantity that you want to estimate. And you want to estimate something like its mean value under many evaluations of some stochastic market model that you have in mind. And the basic way that you want to estimate the price of a derivative is to just run the market model many, many different times with different random seeds, and then take the empirical average of the results that you obtain to form a strong guess for what the risk neutral price, say, of that derivative should be. Now, it's well known that if you want to obtain this price to accuracy epsilon, and here I mean in relative terms, then it's well known that you have to run this classical model in general order 1 over epsilon squared times. And this is in theory efficient because in theory this is only a polynomial dependence on epsilon, but in practice this can be quite expensive, right? So obtaining relative accuracies of, say, 10 to the minus 3 to 10 to the minus 5 in financial applications, you could have to run this market model millions to billions of times, and in certain applications that cost can be prohibitive. So fortunately, quantum computers do offer a very general speedup of Monte Carlo methods. So this algorithm goes back to Broussard et al. In 2002, though it was most recently in the more general form in the paper of Ashley Montanaro. And the quantum speedup is a quadratic speedup. So the statement is now that quantum computers can perform epsilon accurate Monte Carlo simulations using only order 1 over epsilon runs of the market model instead of 1 over epsilon squared. And this quadratic improvement can be quite large. So for instance, this would take millions of runs into only thousands of runs. So the kind of raw speedup obtained by this algorithm could be 1000x or more. And this could really have a major advantage for the first people to apply this technology, because it could allow for real-time or close to real-time pricing of very complicated derivatives or performance of very complicated risk analysis functions that one would not be able to do with classical Monte Carlo methods. Now, the challenge with this quantum algorithm from Monte Carlo is that it's actually extremely difficult to run in quantum hardware. And this is because of really 2 particular bottlenecks in the quantum Monte Carlo algorithm. Okay, so the first bottleneck is that you have the stochastic market model that you're trying to evaluate the price of your derivative with respect to. So you have to be able to run that market model as a quantum circuit natively in quantum hardware. So it's not like you can have an optimized classical CPU implementation of this market model. You have to actually implement it natively in the quantum hardware. That itself is already fairly challenging for more complex market models. But even more critically, the quantum Monte Carlo algorithm has another bottleneck, which is that it's not an algorithm that is natively parallelized. So in particular, you have to be able to run this market model on your quantum computer not only once, but actually many different times in series in order to capture the speed up. So it's not like you just run it only once on each instantiation and then terminate your quantum computation. It has to be run in this extremely deep quantum circuit. And what this ends up meaning is that because this algorithm requires very deep circuits, it means that if you wish to run this algorithm on real hardware in such a way that's performant, then this requires very high quality qubits in order to run. In fact, we estimate that the quality of qubits that would be needed to run this algorithm is at least a decade away. And there have been some attempts to try to improve this this resource requirement for running this algorithm. Namely, there have been some works producing what are called QFT-free or quantum Fourier transform-free Monte Carlo methods. And these provide a slight improvement in the depth of these algorithms, but they don't overcome this fundamental limitation that you have to perform these evaluations of this market model in series and have extremely high depth circuits. So here at QC-Ware, we've been working to try to remove this bottleneck. And next, Anupam is going to tell us about his work in trying to decrease the depth requirements for running this quantum Monte Carlo algorithm.
Thanks, Adam. So let me tell you about some of the shallow Monte Carlo algorithms that we have been developing at QC-Ware and the kind of advantages they offer over the standard Monte Carlo algorithm. So, so the method that I'll tell you about has many advantages. Like most importantly, it can obtain speedup even with low depth quantum circuits. And as a result, it can tolerate many orders of magnitude more noise than the standard algorithm. It is not a fully serial algorithm, like there's a way to parallelize it and run many copies together. And most interestingly, it trades off some of the quantum speedup that you obtain for better noise tolerance. And there are lower bounds that show that this trade-off is almost optimal. So as Adam said, the current Monte Carlo methods are at least a decade away. And with the shallow Monte Carlo methods, we bring forward the point where quantum computers will be able to provide speedups for Monte Carlos, but so it's much closer to the near-time devices than before. And we think that it's about 5 to 10 years away in terms of implementation. So on the next slide, we'll show a schematic which has the quantum hardware progress expected on the x-axis and the kind of speedups that you expect on the y-axis. And the schematic will try to illustrate how our methods try to bring forward the date of application of the Monte Carlo, quantum Monte Carlo algorithms. So as you can see, like in the very top right corner is the best known application of quantum computing, which is breaking encryption using Shor's algorithm. And for that, you require extremely high quality qubits. It's more than a decade away, but the impact is very high. So the standard Monte Carlo method does not require as many resources, but it provides instead a polynomial instead of exponential speedup. So it has moderate speedup, but it still does require very high quality qubits and is at least a decade away. The QFT-free Monte Carlo methods that Adam mentioned improve this somewhat. And the shallow Monte Carlo methods that we are developing trade off some of the speedup. Like you can see the speedup for the shallow Monte Carlo methods is a bit less than the standard algorithm, but they bring forward the implementation of this algorithm by quite a lot. So, so because of the higher noise tolerance and the lower depth circuits that you need for these algorithms and still manage to get a speedup, we would expect that this should be performant within the next 5 to 10 years. So, so on the next slide, we'll show some calculations of how these, how the shallow Monte Carlo algorithms perform with respect to simple, moderate, and highly complex derivatives. So for these calculations, we use some market model circuits with where simple, moderate, and highly complex refers to the number of gates that you use for a single run of the market model. So the simple derivative uses 10 to the 3 gates. The moderate one uses 10 to the 5 gates, and the highly complex derivative uses 10 to the 7 gates. And for all these, we computed the noise rates that would be required for the quantum hardware to make this algorithm performant. So for the standard Monte Carlo methods, you can see that these rates are quite high. So it's like 10 to the minus 10 even for the simple derivative. And for the complex ones, it's like 10 to the minus 14. And as you can see on the slide, the QFT free Monte Carlo methods improve this by a bit, like they are 10 to the minus 9. It's one order of magnitude, but the QC-Ware's shallow Monte Carlo algorithm makes quite a significant improvement by many orders of magnitude. So it's 10 to the minus 5 for the simple derivative, and 10 to the minus 7 for the moderate one, and 10 to the minus 9 for the highly complex one. So let me warn you that the current error rates are in the range of 10 to the minus 3. So the current hardware is still not good enough to be able to run even the shallow Monte Carlo algorithms. But they might be some of the first ones to be performant on the quantum hardware as it comes up. So on the next slide, we will take a slightly different perspective to illustrate the kind of speedups that we expect from the shallow Monte Carlo algorithms. So here you see on the x-axis, the effective 2-qubit error rate. So this is a measure of the quality of your quantum hardware. So if it's 10 to the minus 10, it means you have really good quality qubits and the noise rate is really 10 to the minus 10. But there's another important factor to consider when we compare quantum to classical machines. So the clock speeds for the quantum machine is usually much slower than the clock speed for the classical computers. So there's this slowdown factor that's inherent because of the slower quantum speeds. So on this plot, we have the quantum clock speed on the y-axis and the qubit error rate on the x-axis. And this in general is a map of the hardware space. So the big blue rectangle that you see on the right is the regime where you expect speedups from the standard Monte Carlo method. And the light blue triangle that you see is the regime where you expect speedups from the QC-Ware shallow Monte Carlo method. So you can see that this method unlocks a new regime for the hardware speedups. And we can also see like where the current hardware stands and what progress we expect in the future. So let's so the current hardware is not in the regime where we can achieve speedups as of now, but there are two possible directions in which improvements can go. So the first is the quality of qubits gets better, like the noise rates improves. And then from the gray area, one moves to the left into the blue areas. And there's another alternative, which is that the number of qubits grows, and then one can use quantum error correction to boost the quality of the qubits, but at the expense of slowing down the clock speed of the quantum computer. So this is represented by the line with slightly upward slope. So starting with the green star, which is the current hardware from now, like future approaches will push that, the hardware parameters towards the blue region where one can expect speedups. And as you can see in either case, like whatever approach the hardware improvements take, it is quite likely that it will hit the light blue region first, and the shallow Monte Carlo kind of methods would be the first to give speedups for quantum Monte Carlo methods. So I'll end by telling you about a paper that we have on this, which will be appearing the next week. So this is a paper which was carried out in collaboration with Goldman Sachs, and it's about low depth amplitude estimation algorithms, and it covers the shallow Monte Carlo algorithms that I talked about in this webinar, and it should be available on the archive on the next week. So with that, I will move on to some of the other applications of quantum computing to finance, and we'll talk about machine learning. So quantum machine learning, one of the first questions that arises is, why should we consider it, as classical machine learning is quite successful on its own and is highly performant. So classical ML, as we all know, has been very impactful in most sectors of the industry and also in finance. So the answer would be that full-scale quantum computers are known to provide significant speedups for ML. So including problems like recommendation systems, regression, classification, and clustering, and a wide number of things. And also closer to the near-term era, we have heuristics like quantum neural networks, which are based on variational circuits. So these don't have provable guarantees, but one expects that when one runs them in practice, you would get good results. And QC-Ware's goal in this sector is to bring the QML with the provable guarantees closer to the near-term implementations. So I'll describe again some of the efforts that we have been making on this front and where we stand on this currently. So one of the main efforts that we have making is about data loaders, which the next slide will show. So when we talk about ML, the data is mostly classical, and one needs a mechanism to load it in a way that's accessible by the quantum computer. So for this, the previous known solutions used the QRAM or the quantum random access memory that was considered speculative and didn't have a hardware implementation. So at QC-Ware, we have developed instead parameterized circuits for loading the classical data into quantum states. So let me tell you about the resource requirements that one needs for doing this. So if you want to deal with capital N dimensional classical vectors, then with QC-Ware's loader, you would need n qubits, a circuit of log n depth, and just n-1 gates. And we also have an optimized loader, which uses square root n both on the qubits and the depth. So this does bring the quantum machine learning algorithms quite closer to the NISQ era than you would expect. So for examples, vectors of a dimension 1000 would require only about 100 qubits and 100 depth, and these are reasonable parameters that you might expect to have in the next 5 years, let's say. So with this solution to the input problem, the schematic of machine learning changes quite a lot, as we see on the next slide. So again, this is the similar slide as to the Monte Carlo. There's the quantum hardware on the x-axis and the speed up on the y-axis. And then you see all the quantum machine learning applications here. So the gray dots tell you where they were when we had to rely on the QRAM or some other device which was not available. And we would consider that they were more than 20 years away. And now with the data loaders, many of these applications have moved forward quite a lot. So for example, we have classifiers and clustering, which are quite close to the near term. Like we even have some hardware experiments for classifiers that we run on the IonQ machines that I'll talk about in the end. And then the other applications have moved forward, but of course, a lot of work needs to be done to make them more near term, and that will be a work that we'll be carrying on in the future. So yeah, so I'll now tell you about okay. So this slide again tells you about the impact of data loaders. So this compares the previous approaches for loading classical data into quantum devices. And you see that they had major bottlenecks, like either they had very high qubit counts or very high circuit depth. And QC-Ware's data loaders, which are available on the Forge platform, are much better compared to these. For example, the optimized loader needs only both 100 in qubits and the circuit depth to deal with 1000-dimensional vectors. And we hope that they should be implementable on the existing hardware in the near term. So one very nice application of the data loaders is quantum distance estimation that we'll talk about next. So this deals with a problem that comes up very often in machine learning, which is to estimate efficiently the inner product between two vectors x and y. So for this task, one gets a very efficient quantum circuit by just composing the data loaders for x and the inverse loader for y. And this we think will be a component of near-term quantum classification and clustering algorithms. So with the data loaders and distance estimation, we were able to run some experiments on the IonQ device. So let's go to the next slide. So this implements a nearest centroid classifier, which is one of the most basic classifiers in machine learning, on the 11-qubit IonQ device, using our data loaders and distance estimation circuits. And it's a collaboration between QC-Ware and IonQ. And this again will be available sometime the next week. So yeah, so I tried to tell you some about the work we are doing in quantum machine learning. And now I'll hand over to Adam to tell you about optimization in finance and what QC-Ware has to offer on that side.
Great, yeah, thanks, Anupam. So Yeah, so I'll now cover the third and final area of applications of quantum computers to finance, namely to the problem of portfolio optimization. So in portfolio optimization, the goal is to try to maximize one's returns at a given level of risk. This is a canonical problem in computational finance. And the computational difficulty of this problem varies widely depending on what sorts of constraints you face in your portfolio optimization problem. So the most general form of portfolio optimization, which is unconstrained, the one that was originally formulated by Markowitz back in the 50s, actually turns out to be relatively easy to solve classically. It ends up reducing to solving a single linear system. But the complexity gets substantially more difficult if you start adding in more realistic constraints. So for example, if you apply linear constraints to your portfolio optimization problems, such as requiring the portfolio to be long only, or setting a maximum upper bound on how much can be invested in certain assets or assets classes, then this in general becomes a convex optimization problem, which still admits a polynomial time classical algorithm, but one which is harder than the unconstrained case. And also, if you impose further constraints like integer constraints, such as you can only purchase integer units of assets, then this becomes a much more challenging problem. It's an NP-hard mixed integer program, and it then becomes a much more challenging problem because it becomes very combinatorial in nature rather than based on a smooth and convex mathematical structure. So there are quantum algorithms for all three of these variants of the portfolio optimization problem. So in particular, for the unconstrained case, it's known that quantum computers offer a polynomial speedup for this. This was coming from the work of Harel, Hasidim, and Lloyd from over a decade ago about how to speed up quantum solvers of linear systems. And for the more general constrained case, there was more recently a paper of Anupam on this call, Jordanis Karanidis, who's also at QC-Ware, as well as a collaborator, showing that there's also a polynomial speedup for these more general constrained convex variants of portfolio optimization as well. And this speedup is actually based on a lot of the same quantum linear algebra tools that Anupam was talking about in his ML section. So those same methods like quantum data loaders and these sorts of linear algebra-based methods are also useful in the portfolio optimization case. On the other hand, for the combinatorial problem, this is a much more difficult problem. So because this problem is NP-hard, we don't expect there to be a general efficient quantum algorithm for solving this problem for all instances. So instead, what we have in the case of combinatorial optimization is quantum heuristic algorithms, such as the quantum annealing approach, as well as the quantum approximate optimization approach. And these are two quantum heuristic algorithms which just work on different types of quantum hardware. So the annealing approach works on special purpose hardware called annealers, such as the D-Wave device, and the QAOA, Farhi et al., this runs on circuit-based model machines. So this is the machines such as the type that Google and IBM and IonQ and many other companies are creating. So for these algorithms, we don't know if and to what extent they will provide a speedup for portfolio optimization. The appeal of these algorithms is more that there's something that we expect to be able to run in the relatively near term. So these might be one of the first approaches that one might take in trying to use a quantum computer to tackle portfolio optimization. So QC-Ware has been working to develop unique methods in order to provide performance improvements to all of these approaches to portfolio optimization. So in the unconstrained and constrained cases, as I previously mentioned, the data loaders and linear algebra-based quantum algorithmic techniques that Anupam and others are developing here, these also provide similar improvements to the unconstrained and constrained portfolio optimization algorithms. Though once again, these algorithms are still a few years away, as I'll discuss more on the next slide. Oh, sorry. Yes, so with these improvements from the QC-Ware approaches, we would estimate that these algorithms are still 5 to 10 years away, but what these algorithms are really allowing us to do is kind of to optimize the circuit depth and qubit count trade-offs in order to kind of bring these speedups as close to near term as we can possibly do. On the other hand, for the combinatorial portfolio optimization problem, there are kind of two QC-Ware unique methods. The first is the anneal offset method of Adame and McMahon from 2020. This is a technique which is used to improve the performance of quantum annealing heuristics. For those of you who are familiar with the method, it's a way of performing a sort of inhomogeneous driving in the annealer in order to find the ground state solution faster. And on the QAOA side of approach, we have a recent paper forthcoming, in which we're going to provide ways of analytically analyzing and also optimizing the performance of circuit-based models such as the QAOA. So just to give you kind of a broad overview of where this puts us in terms of when will portfolio optimization actually have practical speedups from quantum devices. So the techniques with proven speedups, such as convex optimizers and data loaders, these techniques are all still somewhere between 5 to 10 and 10 to 20 years away. Actually, there's some sense in which these linear algebra-based algorithms for convex optimization are actually more difficult than some of the early machine learning algorithms, which is why we've put it a little further to the right than some of these algorithms like clustering algorithms that Anupam was talking about. On the other hand, we have these heuristics, such as these annealing algorithms and these QAOA approaches. And these are algorithms that we expect will be something that we can try in the next few years, but we don't know to what extent they'll have a speed up for portfolio optimization. The expectation is that they might not provide a very generic speed up, but if they provide speed up, it's going to be something which might occur in certain cases or certain flavors of portfolio optimization, but not others. So that's something that will be very interesting to see going forward. So in fact, QC-Ware has a paper coming out shortly on some of these optimizations and analysis of the QAOA approach. I believe this is expected to be on the archive in the next week or two. So please look out for that. All right, and with that, we'll now switch to answering live Q&A from the audience. So if you have questions for us, just please type it into your chat, and then we'll start going through the questions and answering them one by one. Thanks so much for your attention.
Yeah, so we already have some questions posted in the Q&A function. Let's take this first one. How many noisy qubits would be necessary to capture the speed up? I think this was posted in relation to the Monte Carlo, the shallow Monte Carlo method.
That's an excellent question. So that depends very highly on the quality of the qubits, of the physical qubits that you start with. So if you assume that quantum computers scale by just taking current error rates and then just building more of those qubits, then because those error rates are very high, the cost of quantum error correction in order to improve the effective error rate, that cost ends up being fairly high. So as a result, one might estimate that if you had error rates of 10 to the minus 3, the answer you get is that you would need a very large number of physical qubits in order to run the algorithm and achieve a speed up. In fact, I think a recent survey of Egger et al. Coming out of IBM had an estimate that it would require something like 30 million physical qubits in order to provide a speed up at that particular error rate. Now, on the other hand, if you assume that the quality of qubits improves as you scale quantum hardware, that's to say, if you think that the physical qubits can have lower error rates, then under these more optimistic assumptions, the cost of quantum error correction decrease substantially. And then you could potentially have a speed up with, say, let's say order of magnitude would be hundreds of thousands of qubits instead of tens of millions. So I'd say that it's very difficult to predict what's going to happen in the space. Also, these kind of resource estimates are with kind of current state of the art error correction, and future improvements to quantum error correction could also bring this forward as well as these improvements in qubit quality. So yeah, this is something that we'll just kind of have to see how quantum hardware performs before we know exactly what's required. But this is why we still say that this is at least 5 to 10 years away. What I will say about the near term, the shallow Monte Carlo methods, though, is that by trying to provide a speed up even with an error rate of 10 to the minus 5 to 10 to the minus 6, what we're really trying to do is we're hoping that if the hardware improves more optimistically, as if the hardware actually has lower physical error rates, then you might be able to just barely perform the shallow Monte Carlo algorithm without full-on error correction. And if so, then the number of qubits required drops substantially. So yeah, I hope that's helpful.
Okay, thanks, Adam, for that. Let's take a few more questions here. So one of the questions with relation to Monte Carlo is what do you define as simple versus complex derivative?
Sure. So actually, Anupam, you want to take this one?
Yeah, let me take that one. So the measure of complexity that we use here is the number of quantum gates that you need to run a single copy of the market model. So when we say simple derivative, we mean that you need 10 to the 3 quantum gates for a single copy of the market model, and the moderate one is 10 to the 5, and the complex one is 10 to the 7. So you have to translate your model into a quantum circuit, and the number of gates is the measure of the complexity.
So actually, the question was it was asking whether it's a Euro-Asian derivative. I mean, can you provide like a more kind of specific example? I guess what we call a simple versus a complex multi-asset. What would constitute a simple versus a complex derivative?
Yes, so for all these, you would have a specific procedure for evaluating the market model. For example, the Euro call options are probably the ones that would fall in the simple category. And as the complexity of the operations you need to do to evaluate your model increases, it also increases in terms of the quantum complexity. So if you need
it's
more
not only a function of the
run your model, it would be the same in the quantum setting as well.
I'm just going to add, it's not only a function of the complexity of the derivative you're pricing, but also the complexity of your market model. Like, is it just a log normal random walk, or is it a much more complicated sort of a stochastic evolution? So that can also affect it, as well as the the complexity of the evaluation function of the price of the derivative at the end.
Maybe can we provide like a very simple example of like one of these simpler derivatives like Euro, Asian, and like for a certain amount of time, let's say we are pricing it out for the next, I don't know, 3 months, right? Can you provide like a very simple estimate of how many qubits we would need, the high quality qubits, right? The 10 to the minus 5 qubits. How many qubits would someone need to apply this algorithm and get the speed up basically for a simple derivative?
So the bottleneck is, of course, translating your simple derivative into a quantum circuit. And so it's much of an engineering effort. Like you need to take your market model and translate it into a shortest possible quantum circuit, right? So it also depends on that.
Okay. All right. Good. Let's see. So we have one question. I think it refers basically to the x-axis of some of the graphs we've shown, where basically the algorithms appear as bullet points moving towards the near term. And basically the question is saying, okay, well, how did we come up with the estimate of the years to realize these algorithms on the quantum hardware? How did we come up basically with the fact that we were at 10 to 20 years before, and now we're maybe at 5 to 10 years? If I understand the question correctly, I think that's what they're getting at. What constitutes, I guess another way to think about it is, what constitutes 5 to 10 years away? What constitutes 10 to 20 years away?
So of course, these are off the envelope estimates. Like nobody can really predict what will happen in 20 years. But the rule of thumb is that if we are in the intermediate regime, that's the 5 to 10 years, then we have a few hundred qubits and possibly a few hundred circuit depth. So that's maybe a more accurate way of saying it. And for the ones which we think are a decade away or 20 years away, so they need really high quality qubits that have very low noise rates or are error corrected.
We've already seen from hardware manufacturers, they believe that in 10 years, they might have something like 1 million qubits. And you're also saying that it would be the high quality type of qubit. What is your opinion on these quantum inspired type of devices which implement these algorithms but using classical hardware technology?
So yes, so for the parameterized circuits and quantum neural networks, these are heuristics. Like you have to try them out and see how they work. Like it's very difficult to prove theoretical guarantees on them and to say in advance that they will be provably better than the corresponding classical algorithms. So that's why one of the approaches we are taking at QC-Ware is to try to bring the provable algorithms closer to practice. And of course, like these remain interesting avenues to try out and see as the hardware catches up.
Okay, yeah. So you're saying they're basically heuristics. So we really don't know if they're going to work out or not. I mean, there's basically no proof either way that these quantum inspired approaches on classical hardware will really pay off. They might not, but we just don't know. So how do we handle the scalability issues for circuit-based algorithm for portfolio optimization as the effect of barren plateaus start appearing?
So actually, we are not using quantum neural networks for them. So the algorithms so some of them we talked about use quantum linear algebra. So those are the provable ones. And then I'll pass on to Adam to handle how we are dealing with the heuristic side of it.
I'm not sure if it's been proven that QAOA suffers from barren plateaus necessarily. So I think this is a problem that really occurs most dramatically with neural nets. Like it's coming from the fact that the particular ansatz that they're assuming for kind of what's their first initial guess for what would be a good quantum circuit that would solve this optimization problem is a very generic circuit. And those very generic families of circuits suffer from this barren plateau problem. But I don't believe this is known to happen in the setting of QAOA, where they're actually very structured circuits that you're starting with. Now, there are other problems with QAOA that are going to make it difficult to scale. The main difficulty there is that it's difficult to find the optimal angles for running the QAOA algorithm to provide the best performance guarantees. And I think this is actually just a fundamental challenge for the field. For really high depth circuits, it becomes extremely difficult to classically compute what the optimal angles are. So I think that's still kind of, it's still very much an open problem to solve that as it scales. And this is why, again, we said that QAOA is a heuristic method. We really don't know what's going to happen there in terms of speedups. Whereas on the other hand, these linear algebra-based methods that are a little further away, there we have proven quantum speedup, so we know that those algorithms will work.
Thank you, guys. And why can't we use existing quantum random generators on classical Monte Carlo financial algorithms?
So it's not about random number generation. So it's like estimating the coin flip probability if you're given a biased coin. So a better random number generator will not help you here. So the improvement in quantum Monte Carlo is in terms of the number of samples. So you need 1 over epsilon squares samples classically to get an epsilon error estimate, and the quantum algorithm gives you 1 over epsilon samples instead. So the right measure to think about is the number of samples you need to estimate the coin flip probability, not the random number generator.
Are there prospects for quantum algorithms for recursive expectation values such as least squares Monte Carlo methods?
Yeah, we think like it should be a good idea to explore these. Like what we have right now is a very basic version of the quantum Monte Carlo methods, and it may be possible to use additional ideas and get newer methods which are impactful. So that is something that we should look at in the future, or is a good direction for future work.
So here's another one. Can financial institutions glean value from the shallow Monte Carlo simulation now, even though it's still currently beyond the reach of NISC processors? I think, I mean, maybe I can take this one. So we will be announcing next week our collaboration with, well, actually, we've already talked about the paper here. We'll publish with Goldman Sachs next week. And I think, all of these financial institutions that are essentially investing into quantum computing programs right now, basically, they are looking basically to estimate the value proposition for these approaches, right? And that's why they're basically building these big quantum computing initiatives. And so next week at the conference, at the Q2B conference, we will hear from Goldman Sachs and JP Morgan and BBVA, that constitutes basically the panel, the financial track we have at Q2B, where these institutions will basically say, okay, what exactly are they looking to achieve, and how they're evaluating basically the value proposition, how they're evaluating, the potential return in the future of these algorithms, right? I think that's what we can
so
say.
I'll just add that just to kind of, I'm not sure exactly what was intended by the question, but what I will say is that these classical simulations of these quantum approaches are useful for kind of exploring what might happen with these algorithms as we scale them, but they aren't themselves going to provide any sort of speed up for the problems of interest, just because usually the simulation time, the classical simulation time of running these kind of quantum methods and simulating them on classical hardware, the overhead from that is much higher than the gains one gets in this 1/epsilon squared to 1/epsilon performance improvement. So yeah, so I think they'll be a useful tool for kind of exploring these methods, but they're not going to provide, the classical simulations themselves, of course, won't provide speed ups.
Actually, a related question to this, it says, though simulation of qubits is expensive in terms of memory, how many perfectly noiseless simulated qubits would be necessary for the methods you propose respectively?
I would say it's somewhere in the hundreds to thousands range, but it depends. That's if you're very smart about how you compile your market model to qubits, to a quantum sampling algorithm. I think if you did it very naively, you could end up with many more qubits than that. But I think on the lower end, for the simple derivatives, it would be somewhere in the hundreds to thousands range of perfect qubits.
So here's another one. Did you do a comparison analysis for gate-based and annealers in some of these approaches?
Yeah, no. So we haven't. We don't in the paper, provide any performance of these as kind of head-to-head. They're kind of apples and oranges approaches to the optimization problem. And I think it's challenging even to run the simplest forms of QAOA now on circuit-based machines. So yeah, I think this is still something that remains to be done.
Actually, so there was the second part of this question. So I think the question was also referring to shallow MC, but is it applicable to MC? Can you run any of these Monte Carlo approaches on annealers?
I don't think any of these Monte Carlo approaches are all for circuit-based machines, so they cannot be run on annealers.
Okay, thanks. Can we also use quantum Monte Carlo simulations for reverse stress testing, i.e. looking for the scenarios that contribute to the long tails instead of the other way around?
Yeah, I believe that would be possible. I think that would follow, again, from kind of quantum amplitude estimation based techniques, that you could have a, say, quadratically better chance of finding some tail event than you would with a classical sampler. Yeah. I'm not sure if that's been written up anywhere, but I think that would follow relatively straightforwardly from the existing kind of quantum Monte Carlo approaches.
Okay, so here's another, I think, very interesting question. So it says most algorithms are versions of amplitude estimation, some form of variational circuits, or HHL, right? Do you think the field might be disrupted by a completely different algorithm?
So yeah, so that is a good comment that most quantum applications use one of a bunch of algorithms. So we certainly hope that there are more things to be found, and if you have any ideas, we would be happy to discuss. It's yeah, but there is hope that there are remaining approaches that could be tried.
Okay, great. What are the perspectives on hybrid classical quantum models applied to classical data, parameterized circuits, quantum neural networks, etc.?
So I think we already answered it. Like, these are heuristics, and we think that you need to try them out and engineer them as best as you can, and see how well they do.
Have any of these quantum implementations for portfolio optimization actually been deployed in production?
Not that I'm aware of.
And there's another one that says, it seems as if the focus is solely on speedups. Are you doing any research to exploit quantum effects to do different things computationally, like create new financial instruments?
So not yet, but again, if you have ideas on this front, we are happy to discuss. So
For the QAOA++ approach, for which P was it tested?
Oh, this is for very low P. This is, I think P is 1 or 2. So this is, tends to be focusing on lower P, because this is where we can understand much better what the correct angles are to feed into the QAOA approach.
So we're now at the top of the hour. I apologize for not maybe answering some more questions there that were asked. We're out of time now. We want to be respectful of everybody's time. We'll, as I said, we have recorded this, so we will post it on YouTube. And thank you very much for coming in and attending. We hope to see you very soon at the Q2B conference next week. Thank you very much.